We're going to talk about the alternating series test, and we'll start with what is an alternating series. We call a series an alternating series if the nth term a sub n is of the form minus 1 to the n minus 1 times b sub n, where b sub n is positive for all natural numbers n. What that means is the signs of the terms will alternate. We make sure the b sub n's are always positive, and then the minus 1 to the n minus 1 alternates from 1 to minus 1 to 1 to minus 1, etc. Here's an example. We could look at the sum from n equals 1 to infinity of minus 1 to the n minus 1 times 1. You don't have to write the times 1, but I'm putting the 1 there. That's our b sub n. This is exactly the series 1 minus 1 plus 1 minus 1 plus 1. You can see the signs of the terms alternate. Does this series converge? We can see directly that the first partial sum is 1. That's if we add just one term. The second partial sum is 0. That's if we add two terms. The third partial sum is 1. The fourth partial sum is 0, etc. So for this particular alternating series, we can tell immediately that the sequence of partial sums diverges. It doesn't diverge like many sequences we've seen because they blow up. This one diverges even though it's still bounded because it just keeps jumping back and forth between 1 and 0. It's not converging to any one particular number. Here's another example of an alternating series. If we have minus 1 to the n minus 1 times 1 over n, we're going to be looking at this one more later. This is called the alternating harmonic series. And it should be clear why it's called that. Without this minus 1 to the n minus 1 part, it's the regular harmonic series. The alternating harmonic series has the same terms, only with alternating signs. 1 minus a half, plus a third, minus a fourth, plus a fifth, and we keep going. Now, we're going to see much later, not until near the end of chapter 11, that we can actually find a value for this alternating harmonic series. It converges and in fact will equal this special number, log 2. But as I said, we're going to see that much later. Right now, I just want to mention a few things. It's not going to be easy to find an exact formula. In fact, there's no nice exact formula for the partial sums of this alternating harmonic series. We're going to see in just a couple minutes here in this video how we'll actually be able to tell that this alternating harmonic series does in fact converge. Though I'll repeat, we won't be able to find its exact value until many sections later. I want to talk about an important difference between partial sums when you have a positive term series, that's when all the terms are positive, and an alternating series, where the terms alternate positive, negative, positive, negative, positive, negative, etc. If you have a positive term series, that means that all of the a sub n are greater than 0. Then S1 is just A1, S2 is just A2, A1 plus A2, make sure you get that right. S3 is A1 plus A2 plus A3, and we keep going like that. This sequence, S sub n, will be increasing. Because when you add more terms, and all the terms are positive, the partial sums get bigger and bigger and bigger. So the question, does the series converge, is the same as the question, does this sequence of partial sums, Sn, converge? Since this sequence is increasing, it really boils down to the question, is this sequence bounded? If this sequence is bounded, since it's also increasing by the monotone sequence theorem, it will have to converge. Of course, if it's unbounded, there's no way it can converge because it would get arbitrarily large and the sequence would diverge and thus the series would diverge. So when you're talking about a positive term series, convergence of the series is equivalent to boundedness of the partial sums, and that all depends on how fast these extra things you're adding, in other words, the size of the terms, individual terms of the series, how fast those tend to zero. Remember, if they don't have limit zero, the individual terms, the series definitely diverges. But if the terms do have limit zero, it will make a big difference how fast the terms tend to zero. If they tend to zero like 1 over n, you get the harmonic series that would still diverge. But if they tend to zero faster, like 1 over n squared, or even 1 over n to the 1.04 power, you would get a convergence series. For an alternating series, you have the sum of minus 1 to the n minus 1, b sub n. And remember the way we've formulated it here, all the b's are positive. This is for all n. So this is going to be b1 minus b2 plus b3 minus b4, etc. So the first partial sum is just b1, the second partial sum is just b1 minus b2, the third partial sum is b1 minus b2 plus b3, and we keep going like that. Notice that the partial sums now start with b1, the first term, then they get smaller, then they get bigger because you're adding a positive number, then they get smaller, then they get bigger, so they keep bouncing bigger and smaller and bigger and smaller. It's still possible for them to converge if you have these numbers that get bigger and smaller and bigger and smaller, still approaching one limit. But it's possible for them to diverge even if they stay bounded. So alternating series have this very different sort of behavior. Now, this cancellation also helps to keep the partial sums bounded because you add and then a positive number, then subtract, then you add, then subtract. So it's still possible for the partial sums to blow up if all of these odd index terms, say, are much bigger than the even index terms, or vice versa. But the alternation in signs gives you some cancellation that helps keep the partial sums bounded much more easily than for a positive term series.